Let's start off with a linear function, and we'll do all those things I was mentioning in the last video. Try to find what's the degree, how many turns does it have, how many intercepts does it have, what is its end behavior, how do we write it, and all of that stuff. And again, the goal of the first part of the lecture is just to really try to understand how polynomials behave and how the degree affects that as we get more complex. Because as we talk about a lot of theorems, it can be easier to understand those theorems if we get a lot of the things just about the nature of the graph. And you can always take a polynomial, graph it in your calculator as a way to quickly identify what's happening in the curve. Something that maybe 50 years ago wasn't possible to do, which is why these theorems were a lot more important for mathematicians historically. I mean, they're still important. They're just it's easier. Doesn't mean it's less important. It just means that we can determine things without as much brute force. Anyways, so looking at the first function, the linear function, and unfortunately my tablet turned itself off, so let me get logged in so I can take some notes. We'd say that it's degree 1 because, again, as I said, it's x to the first power. So degree of L is equal to 1. And sometimes you'll see it as written as degree or DEG as a function, but it's not like a standard mathematical function where you would need to know the notation. So don't worry about the notation for that in particular. When it comes to a line never has any turns, it just moves straight. Whereas with higher order polynomials like a parabola, we often say that it has one turn to it because it's not moving straight, it's kind of constantly moving turning in a particular direction. It's not like a sharp turn, it's a constant turn to it. So it's kind of like potato potato, what do you mean by how many turns does it have? But it's like with higher order polynomials, notice that they have multiple turns because it's changing direction more than once. Whereas a parabola just kind of has one change in direction, the arc of its shape as well. So basically notice that this polynomial does not turn. I'll just write turns equal 0 in the case of L of x. Linear functions have one intercept of each, right? It has a single x-intercept, a single y-intercept. So, in the same way we'd say that 2, 0, 0, -3. In the context of polynomials, the x-intercept, and notice that a line can only have one x-intercept because it's straight, right? And only if a function turns could it have more than one x-intercept, which is another property that we're going to talk a lot about. But often we refer to the x-intercepts as the zeros or the roots of the polynomial. So anyways, a linear function will have at most 1, 0, which is just another word for an x-intercept. This one has it at 2, 0. Algebraically, you can always solve these by plugging in 0 on the other side and solving for x. And same thing goes for the y-intercept. The y-intercept's always way easier because there's only ever one. It can't have two because it would not be a function by vertical line test. And the y-intercept always occurs at the constant term. So, and that's, certain terms are easy to figure out. So, we got the y-intercept occurs at 0, -3. And, the x-intercept, we could list all these things out, but let's not waste our time with that. But, I'm just trying to come up with all of the properties of these. And we'll talk about end behavior in a minute. Let's move on to some of the other ones because the point of this is I want to associate the degree of the polynomial to a lot of these things, and there is a correlation between the degree and the number of turns, the number of zeros that a polynomial will have. So looking at the degree 2 quadratic function, we can see that it obviously has two x-intercepts. The location of the x-intercepts is kind of hard to tell just from the graph. You might guess, well, maybe it's 2.5 or something like that. But remember, the quadratic formula can always solve the x-intercepts of a quadratic, assuming you have it written in standard form. So in this case, we have, well, -1/2 x squared. There is no x term, so we'd say b is 0, and the constant term is 3. So we'd have a is -1/2, b is 0, c is 3. We could jam that into the quadratic formula to solve those. And we could use the vertex formula to find the vertex, which is a specific term to quadratics, the top of the parabola or bottom, depending on the sign. Another thing I wanted to talk about as we look at these is the leading coefficient actually affects the behavior of whether the polynomial is increasing or decreasing. Like with a polynomial that has a positive leading coefficient, in the case of a linear function, we call it the slope. Positive leading coefficient means it's going up to the right or increasing, whereas if it were negative, it would be going down to the right or decreasing. And with quadratics, we talked about the same thing. When it has a positive coefficient, leading coefficient, it's upward facing, but when it's negative, it's downward facing instead. And technically, as we talked about with functions and increasing and decreasing, it's increasing from left, because we always define increasing from left to right. When it's a negative leading coefficient, it's increasing on the left-hand side to the vertex, then it's decreasing after we hit the vertex. Whereas it would be exactly opposite with a positive leading term as well. Often we use the term concavity to describe a function which has this sort of trend where it's facing downward or changing from increasing to decreasing. And we'd often refer to this parabola as concave down, another term in calculus that you can define. It's a lot easier to solve at that point in time. And we could look into things like transformations, but we're going to talk more about that a little bit later. But anyways, so in this polynomial, the degree is 2. Let's just kind of sketch down some of these things. Degree is equal to 2 here. The number of turns is just 1. Because at the vertex, it's not moving straight. It's turning towards the right. And obviously, a parabola that's facing the other way would be turning towards the left instead. And this one, it has, if we were talking about how many intercepts or x-intercepts or zeros does it have, notice it has 2 zeros as well. And it only has 1 y-intercept at 0, 3, as we already talked about. So what happens as we increase the degree, and I'll see if you can try to make some generalizations about what you might notice. So looking at the next one, a degree 3 polynomial, which again is sometimes called a cubic function. Notice that it has 3 zeros, again with a degree of 3. And if we're looking at the number of turns it has, I like to look at it from left to right. Notice that it sort of turns to the right at this point at its at that local max, and then it turns left. So I kind of look at an overhead view if you're wondering, how do you know what is left and right? What are you talking about? Sort of like imagine I'm driving in my car, and if I'm swerving around like this, I'm making like a sharp right turn and then a sharp left turn. Though technically it's not sharp, it's smooth. Sharp means something else mathematically, but like a real vehicle could never make a sharp turn, like literally a corner, because of the nature of it, unless you're smashing into a wall or something. But I'm getting off topic. But anyways, we would say it has 2 turns because it turns there and turns there, which often corresponds with a localized or absolute minimum or maximum, like in these cases. So that's an easier way to identify it. And again, notice that we only have 1 y-intercept, as we always will. And looking at the last example, the quartic function degree 4, notice that, so we have a degree 4 polynomial. I'll go ahead and write that down. Degree is 4. The number of turns here, again, I tried pretending that I'm driving in my car. It looks like it's turning to the left, then to the right, then to the left, 3 turns. And if I look at how many zeros or x-intercepts it has, clearly has 4. And at this point, you're probably thinking, okay, I see a pattern there. Each one of these polynomials has a number, the number of zeros it has is equal to the degree, and the number of turns it has is always 1 less. And in general, that's exactly the case. Though technically, that's always the maximum it could have. It is possible that polynomials have less zeros than the degree, because, like, say for example, I'm imagining this parabola. If I were to just move that down a little bit, it would still be a quadratic function, but it would not have any x-intercepts. So, and this is actually a polynomial theorem that we're going to look at a little bit later, and look at a little bit more mathematically and examine, well, how do we actually really prove that this is true, rather than what we're doing is just sort of looking at graphs and examining some patterns. But that's one of the things that we're going to focus on are in the polynomial theorems. But basically, to summarize, the number of zeros a polynomial has is at maximum equal to its degree. It can't have more, but it could have up to that many. It could also have less. And again, like in this case, imagine that I took the cubic function and just moved it up or down. If I move it down quite a bit on the grid, it would change the number of intercepts just based on where it's coming, where that shape is connected to the x-axis. Though the number of turns is the same thing, the number of turns in a polynomial is always one less than its degree. Sometimes it's a little bit harder to identify that, but it comes back as being related to the number of intercepts, right? Because if I had a polynomial that had 3 zeros, then I'm kind of can imagine, well, that means this has to cross here, here, and here, or wherever those zeros are. If it has to be smooth and continuous, right? Let's say it starts off coming from the bottom. Now it's here. That was a very bad joke. No, not even a joke. I don't know. But basically, notice if it's going to be smooth and continuous, it would have to come back. If it has those intercepts, right, it would have to come back to those points. So basically, it has to turn to come back to an intercept, right? It's got to turn again to get to another intercept. So the number of turns is directly related to the number of intercepts. And it's always one less because if we have 3 intercepts, there's got to be 2 turns to connect them, to connect the dots, you know. But basically, that's some of the basic properties. I want to continue talking about what is the end behavior, and basically the end behavior is a way of analyzing. Well, notice that some of the time it goes up to the right, some of the times it goes down to the right, some of the time, you know, left to the down to the left or up to the left. Basically, it's a way of mathematically stating that and examining what we refer to as a limit as we go to infinity. In calculus, it's a very common thing, which there's a lot of relevance and importance to.